Let's talk about radiation. Now, I know that word can sound a little intense, right? But the thing is, it's a fundamental part of our entire universe. It's not some kind of magic, and it's definitely not something to be afraid of. It's just physics, something we can understand and, more importantly, manage. So let's pull back the curtain and really get to know this invisible world. All right, so let's kick things off with the biggest, most fundamental question there is. Is radiation something that's just locked away in labs or nuclear power plants, or is it something that's, well, everywhere? And the answer, absolutely, yes. It is all around us. It's in the ground we walk on, it's beaming down from space, it's even in the bananas we eat. But, and you gotta remember this is maybe the single most important idea we're gonna talk about, not all radiation is created equal. Understanding that difference, that's the whole ballgame. The easiest way to think about it is like this. Radiation has two big families. On one side, you have non-ionizing radiation. This is the lower energy stuff, like the radio waves that bring you music, microwaves, even the visible light you're seeing with right now. Generally, it doesn't have enough punch to mess with atoms. But then you've got the other family, ionizing radiation. This stuff is high energy. It has enough power to literally knock an electron right out of an atom. And because it can change things at the atomic level, that's what we're going to focus on today. Okay, so let's zoom in on that ionizing family. It's time to meet the key players. There are a few main types you'll hear about, and each one kind of has its own personality, its own way of interacting with the world. All right, first up, we've got alpha particles. I want you to picture these as the big, lumbering heavyweights of the group. They're these bulky, positively charged particles. But because they're so big and heavy, they're not very good at pushing through things. In fact, their penetrating power is so low, you can stop them with just a single sheet of paper. Seriously, that's it. Okay, so if alpha particles are the heavyweights, then meet the middleweights, beta particles. These are basically just super fast electrons. Because they're so much lighter and faster, they can zip right through things that would stop an alpha particle cold. A piece of paper isn't going to do much. They can travel a few meters through the air before they run out of steam. And that brings us to the real speedsters of the group, gamma rays and X-rays. Now, what's wild about these is that they're not even particles. They're just pure energy. Think of them like waves of light, but with way, way more energy packed into them. And since they have no mass, they are incredibly good at penetrating matter. They're the hardest to stop by far. So, this chart right here, it just lays it all out, nice and simple. You've got your alpha particles, which, boom, a sheet of paper stops them. Then you've got beta particles, which need something more substantial, like a few meters of air. But then you look at gamma and X-rays. To stop them effectively, you're talking about needing thick layers of concrete or lead. A whole different league. Okay, so we've met the players. Now for the next big question. How do we measure this invisible stuff? And even more important, how do we figure out its actual effect on the human body? Well, it's not as simple as just one number. It's actually a really smart three-step process to get the real story. We basically go on a journey. We start with the raw energy that's deposited, then we get smarter and adjust for the specific type of radiation, and then, for the final step, we factor in which parts of your body are actually exposed. Each step gets us closer and closer to the real biological risk. Okay, so step one, it all begins with what we call the absorbed dose. The unit for this is the gray. Think of this as the starting point, the raw data. It just tells us how much pure energy from any kind of radiation got deposited into a chunk of material, like your tissue. That's all it is, just raw energy. But here's the thing, right? As we just learned, not all radiation is created equal. An alpha particle dumps all its energy in one tiny spot, like a bowling ball, while a gamma ray spreads it out more like a spray. So for step two, the equivalent dose, we adjust for that. We take that raw energy number and we multiply it by a weighting factor, depending on whether it was an alpha, beta, or gamma. This gives us a much better idea of the biological punch it packs. And that brings us to the third and honestly the most important step, the effective dose. Because again, our bodies aren't uniform. Our organs have different sensitivities to radiation. So this final step adjusts for which part of you was exposed. I love this analogy. If the absorbed dose is the raw temperature on the thermometer, the effective dose is the feels-like temperature. It's the number that actually tells you how it impacts you, and it's the one we care about most for safety. Okay, so now that we know what it is and how to measure it, that leads to the really big question, right? How do we work with this stuff safely?
Well, the global scientific community has thought about this a lot, and they've boiled it down to a clear philosophy built on 3 solid principles. And it all comes down to these 3 core rules. They are the absolute bedrock of radiation safety everywhere. First, justification. Is it worth it? The benefit has to outweigh the risk, like a CT scan that could save your life. Second, optimization. You keep any exposure as low as reasonably achievable. And third, limitation. There are hard limits, and you always, always stay below them.
Now, of those 3 big ideas, it's the second one, optimization. That's really the workhorse. It's the one we use day in and day out. And it's all wrapped up in one simple, powerful acronym, ALRA. ALARA. It stands for as low as reasonably achievable. And that phrase, that's not just a guideline. It's the mantra. It's the whole philosophy. It's not about getting to 0 exposure, because that's literally impossible on Earth. It's about being smart, being efficient, and minimizing exposure whenever and wherever it's practical to do so.
So how do you actually do ALARA? Well, it boils down to 3 incredibly simple and effective tools. First, time. The less time you spend near a source, the lower your dose. Makes sense. Second, distance. And distance is like a superpower, thanks to something called the inverse square law. Get this, if you just double your distance from a source, your exposure doesn't get cut in half. No, it drops to 1/4 of what it was. It's a huge deal. And finally, shielding. Pretty straightforward. Put the right kind of barrier between you and the source. Okay, we've covered the principles, we've covered the tools. Let's get down to brass tacks. What's the bottom line? With all this in mind, what do the experts and regulators actually consider a safe level of radiation for the general public? The number to know is 1 millisievert. That's the recommended limit for 1 year. And notice we're using sieverts, the unit for effective dose. And just to be super clear, that 1 millisievert doesn't count the natural radiation we get from the Earth and space, and it doesn't count any medical procedures you might need. This is the limit for everything else. But, 1 millisievert is just a number. It doesn't mean anything without some context. So let's put it in perspective. Look here. A single dental X-ray, that's about 0.05 millisieverts. I mean, it's tiny, right? A tiny fraction of the annual limit. Here's our annual limit at 1 millisievert. But then look at something like a head CT scan. That can be around 50 millisieverts. This is exactly why that justification principle is so crucial. The benefit of finding out what's going on in your head has to be worth that dose. And really, that's what this all boils down to. The goal isn't to be afraid of radiation. It's a natural, powerful part of our universe. The goal is to understand it and to respect it. Because knowledge pushes fear right out the door. So I'll just leave you with this final thought. Now that you know the rules of the road, justification, optimization, and limitation, how does that change the way you think about this invisible world that's all around us every single day?